There is an unwritten law in modern structural engineering that dictates heavy, high-velocity kinetic machines must always be anchored to flat, stable, and predictable foundations. But deep within the jagged, mist-shrouded mountain ranges of central China, civil engineers decided to completely shatter this rule. They launched a multi-million-dollar high-stakes industrial assault on a sheer 2,000-foot vertical limestone peak to build what is now globally recognized as the most dangerous and psychologically punishing roller coaster ever conceived by mankind. This is not a standard amusement park ride built on a cleared plot of land. This is an extreme structural anomaly hanging precariously over a lethal vertical drop, where the track doesn't just loop through the air, but literally extends out into the absolute abyss. To understand how human beings could construct a multi-ton steel beast on the literal edge of a mountain cliff, you have to understand a logistical nightmare that pushed modern construction technology to its absolute breaking point. The story of this impossible build does not begin with the manufacturing of precision steel tracks. It begins with an all-out war against hostile terrain, unpredictable high-altitude weather, and the relentless, crushing force of gravity. The first and most violent phase of the project was the mountain assault. The targeted peak was a jagged, uneven pillar of ancient limestone with absolutely zero road access. Traditional construction vehicles, like multi-ton excavators and heavy bulldozers, could not climb the sheer vertical cliffs. The engineering team had to rely on heavy-lift military helicopters to transport heavy machinery piece by piece to the summit. In a series of high-risk aerial maneuvers, tracking through dense mountain fog and unpredictable thermal updrafts, these helicopters hovered inches above the jagged rocks, while crews on the ground unhooked components of massive crawler excavators. Once reassembled on the summit, the machines immediately went to work preparing the ground. But the peak was too narrow and unstable to support the immense weight and shifting kinetic energy of a roller coaster. Engineers had to literally rewrite the topography of the mountain using thousands of pounds of high-grade industrial explosives. Teams drilled deep blast holes into the limestone crust, packing them with precise charges designed to shear away thousands of tons of unstable rock without triggering a catastrophic landslide that would compromise the entire mountain structure. The resulting detonations shook the entire valley, violently fracturing the ancient stone and blasting the top of the mountain completely flat. For weeks, bulldozers and heavy crews operated just inches away from a lethal 2,000-foot drop, clearing hundreds of tons of jagged debris in a constant, high-altitude battle against severe wind shears that threatened to sweep men and machines over the edge. Once the summit was flattened, engineers faced a terrifying physics problem that threatened to destroy the entire project before a single track could be laid. A high-speed coaster train weighing several tons, traveling at speeds exceeding 80 miles per hour, generates massive, violent centrifugal forces and kinetic energy. When a train tears through a tight loop or plummets down a vertical drop, that energy is transferred directly down into the supports. On flat ground, this energy dissipates harmlessly into a massive concrete pad. On a narrow mountain peak, these violent, shifting lateral forces could easily cause the mountain rock to fracture, tearing the entire steel structure completely off the cliff face and sending it crashing into the valley below. The solution required an unprecedented cliff anchoring system. High-altitude ironworkers, dangling like spiders from thin safety harnesses over the absolute abyss, had to operate heavy, vibrating pneumatic industrial drills suspended thousands of feet in the air. They bored massive, deep horizontal and vertical trenches directly into the living limestone face of the mountain. These were not standard anchor holes. These were deep structural shafts extending dozens of meters into the core of the mountain. Specialized high-pressure pumps were then used to force thousands of gallons of fast-curing aerospace-grade concrete deep into these rock shafts, permanently locking colossal steel anchor nodes into the very bedrock of the mountain. The entire weight of the future roller coaster would not just rest on the mountain, it was now mechanically fused to it. With the foundational anchor nodes locked in place, the most visually terrifying and physically demanding phase of construction began, forging the steel skeleton over the edge of the cliff. Massive crawler cranes were balanced precariously on the absolute edge of the blasted summit, their long booms reaching out over the empty, cloud-filled void. These cranes lifted colossal, custom-twisted steel support columns, lowering them out into the open air, where there was no solid ground beneath them. High-altitude ironworkers, standing on narrow steel beams with a 2,000-foot drop directly beneath their boots, fought a brutal and relentless battle against the elements.
Okay, slowly now. Watch the alignment. Reading stable at 50 meters.
Watch out, move back. Get clear of the load. Incoming, look out.
Watch the left side.
Clear on the right. Hold it steady.
Bring it left just a touch. Watch the alignment. Okay, easy down.
The gap measures 25 millimeters.
25. Noted. Check the tension on the bolts now.
Easy now, bring it down slow. Watch the alignment on the far side. The structural certification inspection. The inspector at a critical point. The stamp.
At that altitude, the wind behaves like a violent, unpredictable weapon. Sudden wind shears can cause a multi-ton steel column suspended from a crane to swing violently, threatening to crush the workers or pull the crane itself off the cliff edge. Blinding mountain fog would roll in within seconds, completely obscuring visibility and forcing workers to weld massive structural joints by sheer muscle memory and technical precision. As the orange sparks from their welding torches rained down into the dark, bottomless abyss below, these crews systematically bolted the massive steel skeleton together, section by complex section. To ensure the safety of the ride against nature's most extreme forces, engineers integrated massive, heavy-duty hydraulic dampeners and specialized expansion joints into the main support columns. These advanced engineering components allow the massive steel structure to flex, sway, and breathe during violent high-altitude storms and earthquakes without snapping or losing its structural integrity. The layout of the track itself was intentionally designed to maximize psychological terror and manipulate the human fear of heights. Traditional roller coasters rely on speed and sudden turns, but this mountain coaster utilizes the natural topography to induce pure, unadulterated vertigo. The track winds tightly around the flattened peak before executing a massive, sweeping curve that leads directly to the main launch platform, which sits at the highest point of the mountain. From there, the track extends horizontally straight out over the edge of the cliff, suspended by massive cantilevered steel beams that project out into thin air. When the coaster train leaves the station, it slowly creeps forward onto this extended platform. For a grueling, breathless 5 seconds, the train stops completely. The riders are held face down, suspended over the 2,000-foot abyss, with absolutely nothing beneath them but a sea of shifting clouds and the distant lethal rocks of the valley floor. The visual impact is engineered to trigger immediate psychological panic. Then, the mechanical brakes release. Gravity takes absolute control as the train plummets vertically over the edge of the mountain, dropping at a 90-degree angle straight down the vertical cliff face. The speed skyrockets instantly as the train slices through the thick mountain fog, tearing past the raw concrete anchors and jagged rock formations at a violent pace before pulling up into a massive, gravity-defying loop that hangs over the canyon. Testing this mechanical monster was a logistical operation evaluated with the same precision as a rocket launch. Before a single human being could step foot into the coaster cars, engineers had to conduct hundreds of hours of high-velocity stress tests using heavy, water-filled test dummies equipped with advanced biometric and kinetic sensors. These sensors measured the exact G-forces, structural vibrations, and stress loads being exerted on both the passengers and the steel tracks. During the initial high-speed test runs, engineers watched from a nearby computerized observation bunker as the empty train plummeted over the cliff face. The data revealed that the extreme wind resistance at the mountain peak was causing the train to lose critical momentum during its vertical drop, creating a dangerous risk of the train stalling out inside the massive loop over the canyon. The engineering team was forced to adjust the track alignment, adding specialized low-friction magnetic launch boosters along the drop sequence to ensure the train maintained a perfect, safe velocity regardless of changing wind speeds or weather conditions. Today, this mountain peak roller coaster stands as a brutalist masterpiece of extreme civil engineering and architectural defiance. It is a multi-million-dollar monument to human ingenuity, a structure that successfully converted a hazardous, inaccessible mountain wilderness into the ultimate proving ground for high-altitude engineering. China didn't just build a world-class thrill ride on this peak. They completely rewrote the boundaries of architectural possibility, proving that with enough steel, high-pressure concrete, and raw human endurance, humanity can build its greatest structures directly over the absolute abyss.